recording. And let me go ahead and show the agenda here so you can see what we have on tap. So first, I just want to quickly remind you of how you can review over the break. And I would really strongly encourage you to do that, to spend some time reviewing over the break. Obviously, you need some time, downtime, and some rest time and relaxation, but to do well on the exam, you do need to do some practice on your own. Generally speaking, most students, just by doing the assignments in class and listening well in class and making sure they understand the material, generally speaking, they have a pretty solid chance of getting a 3 if that's all they do. Because we're covering everything and we're reviewing and we're practicing, but a 3, just so you're aware of how it works on the Physics 1 exam, a 3 basically means you're somewhere between 40 and 55%. It's kind of different from year to year where the cutoff is, but sometimes it's as low as 40%. So if you earn 40% of the points, you would potentially get a 3. It's like I said, it's usually somewhere between 40 and 55%. And then to get a 4, though, it jumps up and it's usually closer to 70% to earn a 4. And then to earn a 5, it's usually somewhere between 80 and 85%. So while you would be very likely, as long as you, I mean, you could have a bad day. You might know a lot and just have a bad day and can't focus or whatever. But if you have a good day and you feel prepared, you're pretty likely to get a 3. But if you want to push it to that 4, you want to push it to that 5 to ensure that you can get some college credit, you really do need to be preparing outside of what we do. You know, we'll cover everything, but you need the practice. And so over break, use that AP Classroom website, watch those daily videos, practice some FRQs. We've done practice FRQs the last 2 Wednesdays, and both times I've given you extras. So 2 weeks ago, we did one and there was an extra one in there for you to practice. Yesterday, we did one, but there were 4 additional ones in that packet for you to practice. So those would be good things to do over the break. And you can decide what fits your schedule and what fits your personality. Maybe you're the kind of person that you don't have a lot going on and you just want to spend like 20 or 30 minutes every day, just do a little bit every day. Maybe you want to take a sequence of days off and just not think about school at all for several days. Well, then just pick one day at some point and just say, well, you know, today I'm going to spend the morning, you know, just prepping for my AP classes and maybe spend an hour or 2 just practicing for AP Physics. So there's no assignment over the break, but strongly encourage you to do some practice. And today we're going to finish up the discussion of that FRQ you were working on yesterday in class. And we're going to go over bits and pieces of worksheets 2, 3, and 4. We'll actually go over all of worksheet 2. We'll go over at least an example of worksheet 3 and kind of point out something about worksheet 4, just so that you can use those for extra practice as well. And during lunch today, I'll put the answer keys up on Axis for those worksheets so that if you do choose to work on them over the break and do some of the problems that we don't talk about, that you could check your work and see if you're on the right track. But that is, again, a strong encouragement. There's no assignment, but I would strongly encourage you do some practice over the break. Often, almost every year, I've given an assignment over this break, but because of the way they've changed the exam, and I don't know if you've heard, but they've also given more flexibility to when you can take it and how you can take it. So we're still trying to iron out what Oaks is going to do with that new information because it just came out this week. But there's 2 additional dates to choose from. And one of them you can, the first original date is a paper pencil version. The second new date is you can do either paper and pencil or online. And the third one you can do online only. And that's for physics. For other subjects, it's different. So they've made it different for all the different AP subjects. It's not the same, but that's how it is for Physics 1. So I sent an email and asked our administrators what they thought they were going to be doing. And they were actually having a meeting yesterday to try to figure out what their plans would be. So after the break, we should know more and I can give you some more details. But because you have more flexibility on the day you actually take the test, and because they've cut out the last 2 units, I don't feel like I need to give you a formal assignment over this break. But do encourage you to take some time and review. So let's go ahead and jump back to that FRQ discussion. Yesterday when we were going over it, let me switch the share here and actually open that up. We were looking at the second question from Unit 2, and it's about this spring connected to a block, and the block is bouncing back and forth. And I want to make sure that we may have rushed a little bit through A and B, and you might not have had a chance to get all your questions answered or asked. So before we move on to C and D, do you have any questions about part A, where they were asking what the net force is, or part B, where they were asking you to graph the net force? All right, not hearing any questions. So hopefully that means that what we were able to cover yesterday was enough for you. Just in a quick review, the first part of telling about the net force in terms of its direction and what it was is just worth 1 point. And then the graph, we talked pretty directly and for quite a while about this. Remember, you can actually earn some points for a wrong graph. If there's any aspect of it that's right, they break it down this way. So that's part of the preparation and the practice, is looking through these rubrics and getting comfortable with, oh, these are the kinds of things you get points for, and these are the kinds of things they're looking for. And that's where the practice comes in. The more practice problems you do, the more comfortable you are with the test, the more you can predict what they're going to ask. Now, part C, this is what your graph for part B should look like. You should have a straight line parallel to the force versus displacement line that they gave you, the dashed line, and it should be below. So to earn all 3 points for the graph, you would have to have all 3 of those things true. It should be below, it should be straight, it should be parallel to the dashed line. Now for part C, it asks you to confirm whether your graph supports the other parts. And so this is another example of how College Board tries not to double penalize you. And so you should never leave a question blank. So it says here, 1 point is earned for providing a claim that addresses the graph at an X value of 0. Even if your X value is wrong, let's say you didn't have it as a negative value, you had it as a positive value. As long as you provided a claim that told why and it was consistent with your claim, even if it's wrong, you earn that point. For the second point, earned for providing a claim that is consistent with your answers of A and B, and then whether you picked yes or no in part C. So again, as long as your answer is consistent, even if it's wrong, but if it matches what you put for A and B, you can actually earn both of these points when you've been entirely wrong with everything you've answered prior to this. Okay, the key is that you're consistent. So, because you might have some misunderstanding that led you to a wrong conclusion, but then the rationale for what you did use might actually be right. And if it matches, you get these points. So this is kind of a strange thing that you also have to get used to, that I found a little more frequent in physics compared to my experience with chemistry and biology. So this is one of those areas where never leave something blank. Give it an answer, because you might earn some credit even if your prior work was wrong. Any questions about part C? This is basically just providing rationale for why you graphed it the way you did in part B. All right, you can see that their example response that would earn 2 points says the graph indicates a negative net force at 0 displacement, consistent with the leftward net force predicted in part A. So that's what they're looking for, that you say why your X position was negative, and enforce or reinforce that it is consistent with what you said in part A. So you don't need long answers necessarily. They just have to be consistent. Now for part D, for part D, here's the scoring, but let's go back and see what that question originally was here. So in part D, just to make sure you're understanding the context, this block is oscillating back and forth. So the spring initially, it's like they pushed the box all the way up against the spring and then let go. And the spring would expand and push it across the surface, and eventually it would stretch the spring and come to the limit and start pulling backward. And it would come backward and start to compress the spring until it reached its limit, and then push it the other way. And it would just keep bouncing back and forth, oscillating back and forth as this spring compresses and stretches. But because there's friction, it wouldn't go back all the way to where it started, because the friction is going to be stealing some of the energy from the system. And we're going to be focusing a lot on energy after a winter break. And so that'll make even more sense when we dig into how we determine energy. But you can probably just conceptually understand that friction is stealing some of the energy here. So it's not going to keep going to the full extreme ends. It's going to go less and less and less and less, and eventually it's going to stop moving. But it has the potential, because there is friction, to stop moving someplace other than the zero position where the spring is relaxed. And what they're saying is, at this point, the friction was great enough and the spring force was weak enough that it just came to rest and quit moving. And you can see it's not at the zero position where the spring would be relaxed. So if this is the scenario, this is the image, Johnny, which would be the direction of the spring force, left or right?
To the right.
Is the spring pushing or pulling here?
Oh, sorry, it would be pulling, because it's, yeah.
Yeah, it'd be pulling because it's just sitting at rest. So it's no longer pushing it away. It'd be pulling it back. And so, Sally, what direction would the friction force be at this point if the spring's pulling it to the left?
To the right.
To the right, because friction opposes the motion. So the spring will be pulling it to the left. Friction will be resisting that pull to the right, and that's why it froze. That's why it stopped. Does that make sense? So for number or letter I, it says on the dot below, which represents the block at rest, to the right of that zero position, draw and label all the forces. Now, one thing about the rubric that I want to mention here, I don't know if they just shorthanded the rubric a little bit, or but based on my experience grading these exams in the summer, what they've drawn here as an example response would not earn full credit. And so I'm a little surprised. I don't know if they just forgot to type in the labels or what, but even based on the wording of the rubric, and like I said, based on my experience grading these exams, I don't think you would earn full credit for having just the arrows drawn without labeling what those arrows represent. In fact, based on my experience, I would say this would earn 0 points, even though it shows all the forces, doesn't tell you what any of them are. And so I would say you'd either need to label it, or you need to give some sentences to describe what they are. And I think it'd be easiest just to label it. So my recommendation, don't just draw the arrows. And you can see in the rubric, it says it gives you 1 point for showing that there's an upward and a downward force that would be balanced. So if I were drawing this and I was making sure that I had everything needed, I would add that this should be the normal force, and this should be the weight force, and they would be congruent. Then I would be sure that they would understand I knew what I needed to know about those vertical forces. It's only 1 point for those combined. And then for the horizontal components, I would say, well, in this case, we've got the friction, which is resisting the slide, and we've got the spring force, which is pulling it back, trying to pull it back to the relaxed position, the zero position. And because it's sitting still, there's no acceleration. So those would also be congruent to one another. And so I would, if I were doing the test to ensure that I would get all the points, I would label those and also show the congruency. Any questions about the free body diagram there? Okay. If we go on to the last part, then let's scroll back up and read what it asks again, so we're clear. So part II, section 2 here, derive an expression for the maximum displacement possible for the block that will allow the block to still remain at rest. Express your term and answer, express your answer in terms of m, k, mu s, and physical constants as appropriate. So when they have a phrasing like this, You don't have to use all of those, but those are the only ones you can use. So you can't add other variables unless they're physical constants like G, since it says and physical constants. But you can't use like Fn or other things. You have to get everything converted to these variables. Now, the reason they're saying maximum displacement possible for the block, if you think about static friction, if I'm sliding a dresser across the floor, if I just push a little bit, the static friction resists and it doesn't go anywhere. But the static friction will just match my pushing force, which may not be what it's capable of matching. If I push with one finger, it's for sure much more capable of resisting more force than just one finger. If I start pushing with one hand, it probably still can resist that force, yet I'm applying more force, so the static force would have to be greater. And then if I lean into it and start pushing with both hands, now the dresser starts to move. But there's a maximum value where the static friction can no longer stop the other forces. And so that's what they're saying is, if this was bouncing back and forth and it just came to rest, it's going to come to rest where that matches, and it's at its maximum static force, or it's at its maximum static friction. You could just pick the block up and put it down in different places, and you could put it in a lot of places where it wouldn't slide, where the friction would be enough to not let it slide, but it wouldn't necessarily be maximum unless you let it come to rest on its own naturally. So that's all they're saying is, when would this maximum static friction, which is what we use the equation to calculate, mu Fn, when would that occur? So don't get too confused about that maximum stuff. Just recall that the static friction can be any amount, maximum or less. But what we calculate with the equation is the maximum value. All right, so we need to have mk, coefficient of friction, and physical constants. And because the block is not moving, which of these variables can we right away recognize we will not need?
Mu k. Or
We do
mu
not
s.
need, yeah, we do not need mu k, because mu k is what?
Kinetic friction.
Coefficient of kinetic friction. Kinetic friction means it's sliding, and it's not sliding, it's at rest. So we don't need mu k, but we will use the others. All right, so there's a couple things I want to highlight about the key here, the rubric. The first point is for identifying that the spring force and the friction force would be equal. Now, if we look over here on the next page, they show it with a sequence of algebraic steps. So they start with saying, well, net force is equal to MA, and we're just talking about the horizontal components right now because the vertical components are irrelevant in terms of the friction, or in terms of the spring force. And the net force would be spring force minus, sorry, the friction force minus the spring force, but it has no acceleration, so there's zero when you and for the A, and so the friction force minus the spring force equals zero, and so then therefore the friction force equals the spring force. So that's a way you could kind of step by step prove it, but you could just say the object is not moving, therefore there's no acceleration. Because there's no acceleration, there's no net force. Since there's no net force horizontally, the friction force and the spring force must be equal. So you could just use words. You wouldn't have to show it in a sequence of steps like this. Both ways would be fine. The second point is for indicating that while they're equal, while those two forces are equal, you know that the spring force is calculated by taking k times x, and you know that the friction force is calculated by taking coefficient of friction times the normal force. And then this third part is showing that the normal force can be replaced with mg because the vertical forces would be balanced. So you have to show your understanding of all three of these things. And you, again, you could say it verbally that the equation for spring force is kx, the equation for friction force is mu s times the normal force, and it's static friction because it's not moving, and that the normal force is equal to the weight since the vertical forces are balanced. So you could use sentences or bullet points to explain that. They have used just straight up algebra. So first they substitute kx for the spring force, then they substitute coefficient of friction using the s to emphasize it's static times the normal force, and then they recognize that that would be the maximum displacement because the static friction would be maximum when we use this equation. And then they just solve for X. And then down below, they show that vertically speaking, so the vertical Y force is equal to m times the vertical acceleration. And the vertical forces are normal minus weight. And yet there is no acceleration, so that's 0. Normal force equals weight force, normal force equals mg, and then we can substitute that in. So again, they're showing it in a sequence of algebraic steps, step by step. But what I'm saying is you could explain this in words and be sufficient. And as long as you do explain how you know that the horizontal forces are equal and how you know the normal force is equal to the weight, by saying there's no acceleration in the X dimension or no acceleration in the Y axis, those kinds of phrases, that's sufficient. But you would need to have all of these conclusions with supporting either algebra or sentences or bullet points. Now, this is not one of those paragraph linked response questions, so it could just be bullet points. It doesn't have to be complete sentences or full paragraphs, but it does need to be complete thoughts. So you do have to not just say spring force equals friction force. You have to explain how you know that either algebraically or with words. So any questions on part D, the II, the second part? My suspicion is that part C and D were actually easier than part B with the graph. Most students find part B the hardest part of this question, trying to figure out that net force graph. And sometimes, again, students will get to that part and think, oh man, I don't know how to do this graph. And so they think they're not going to be able to do the rest of it either. Don't let yourself get psyched out. Just because you can't do part B with the graph or you're not sure about part B with the graph, skip it for that time and go on, because you can answer part C. Well, not really part C, but for sure part D, you can answer without having that graph done in part B at all. And then if you just end up saying, I have no idea how to do part B, just draw a graph that you think that you can give any kind of rationale for. And the graph could be completely wrong, but you might earn partial credit. And if your rationale matches, even if it's in the big picture wrong, you can still earn partial credit. So again, don't leave things blank. Give it your best shot. All right, so that is good for that one. Again, I would encourage you, go through the other 4 free response questions that are in that handout. Take the opportunity to practice those as well. All right, let's move on to worksheet 2. So go ahead and get worksheet 2 out. And we're going to check how you did on the first 2 parts and see what you came up with for the first 2 parts of worksheet 2. All right, so what we're going to do with this one, I'm going to show you parts of the key so we can just have some conversation about it. And then I'm going to ask some of you to describe how you were able to solve other parts of it. So we'll have some just conversation, discussion, and some student explanation kind of interspersed as we look through these. And then once we're done with the first 2 questions, we'll put you in breakout rooms and see if you can figure out 3 and 4. And then we'll come back and have you explain parts 3 and 4. So let me go ahead and start sharing the screen of the key for the first part, because we'll just talk this through. Let me scroll it back up so you're not seeing the answer to the last question. All right, so the first 2 questions on here are really a review of what we covered in our notes. And so part A says a car travels through a valley at constant speed, though not at constant velocity. Explain how this is possible. So how can the speed be constant but not the velocity? That's because the direction's changing. And so we've talked about that quite a bit. And then it says construct a qualitative motion map for the car. So qualitative just means you don't have to give any numbers. Just show us the relative size of the vectors and the directions that they point. And so it helps, I think, to draw the kissing circle, because then you know where the center of the circle is, and then you know which direction the acceleration should point. On an FRQ, you wouldn't have to show the kissing circle. It's more of a tool you can use to help make sure you're visualizing it properly. The velocity vectors should all be tangent to the circle, and they should all be the same length. Now, how long they are is sort of unknown. We don't have any numerical data, but they should all be the same length because it says they're going at a constant speed. The reason that there's an acceleration is because while the speed is constant, while the length of the arrows is constant, they are constantly changing direction, and velocity is a vector. And then for the acceleration vectors, again, there's no magical thing about where they put them, but the key is that the acceleration vectors should all be pointing to the center of the circle, because the car is being accelerated in this curve towards the center of the circle. And however long you draw the acceleration vectors, they should all be constant, because in this course, we only study uniform circular motion. And if it's uniform circular motion, we've got a constant radius, constant speed, and therefore a constant acceleration. All right, questions about A or B? Thinking through what's happening here. All right. For part C, is the car accelerating? What direction is the car's acceleration? Well, we've kind of answered that in the picture, and we've kind of answered it in part with what we said in part A. Here is what the key says, just so you can sort of cross-reference if you have something similar to this. The car is accelerating because the direction is always changing. At the bottom, the acceleration is upward. I know because the car is traveling in a curved path, and the center of the circle, the curvature produces, called the kissing circle, is above the car. At the other locations, it's accelerating perpendicular to the tangent at that location towards the center of the circle. So I don't know that that's the best wording, but it's sufficient. It covers everything. Hopefully you have something similar in nature to that. And then for part D, construct a qualitative force diagram for the car at the moment as at the bottom of the valley. Are the forces balanced? Justify the relative sizes of the forces. So this one, it is qualitative. So again, you don't have to give any numbers. Ethan, describe for us, what does your free body diagram look like for 1D?
It's a dot with a force of weight or gravity pointing downwards and a larger normal force pointing upwards.
All right, good. And that is what we should expect here. They've also shown that they are declaring upward to be the positive direction. Not super critical for this question, but kind of a good practice to always think about whether that's an important factor. And we'll see in some other problems we talk about today where it does become pretty critical. So that is how your free body diagram should look. We know that the normal force has to be greater because the car and the person in the car are being pushed back to the center of the circle. So if we think about the car at the bottom, the car's inertia wants to keep going downhill, but the road is not allowing it to continue to go downhill. So if the road was flat, all it would have to do is just support the weight of the car. But at the bottom of this curve, it has to support the weight of the car, and it has to provide additional force to turn it back to the middle of the circle. So it's carrying the weight and turning its direction. And since it has to do both of those things, it's going to be the weight of the car plus some additional force, which means the normal force is going to have to be greater to cause that center-seeking acceleration. Any questions on number 1, A through D? All right, so for part E, we're going to have, for those of you in the Zoom, put your answers in the chat. For those of you in the room, we'll have some of you share potentially as well. What answer did you get for part E? The question says, find the magnitude of the centripetal force. So just type your answer into the chat if you're in the Zoom. And if you're in the classroom, just be prepared to share your answer. Hopefully some of you got an answer for E. Got one person telling 30,000 newtons. Sally's giving us her answer. What about some of the rest of you? What'd you come up with? Johnny has the same. Aiden has the same. All right. Sally, talk us through how you came up with that 30,000.
I did the mass times the velocity squared over the radius. So 1,200 kilograms times 25 meters per second squared over 25. And I got 30,000.
All right, good. So I'll scroll down here and show their setup. They do an extra step here, which isn't really necessary for part E, but it actually helps answer part F. So I'm not sure why they include it here necessarily, but so the first line here, FG equals mg, that's actually part of F. So, but the second row here is really what we need to focus on to answer part E. The centripetal force in this case is the net force, and it's the difference between the normal force and the weight. And because it's how much force is required to push it back to the center. So we know that the acceleration centripetally is v squared over r. And we know if we just multiply acceleration times mass, it gives us net force. So just like Sally said, we would write it this way. Now this doesn't show sig figs necessarily. How many sig figs should my answer have?
2.
2. So I could write this as 3.0 times 10 to the 4th. Or I could just put a line over the 0 that's right next to the 3. Because when you put a line over a 0, it shows in science, it shows that that 0 is significant. So I could put a line over that 0 right next to the 3, or I could write it in scientific notation as 3.0 times 10 to the 4th. All right, now for F, now it's saying, okay, well, you already did a qualitative force diagram earlier, and Ethan talked us through how he drew it. Now they're saying, okay, we'll make it quantitative. You've got some numbers now. Where do we put those numbers on the list or on the diagram? So let's go back to Ethan since he gave us the qualitative one. What numbers did you put on the weight and the normal force for this step?
For the weight, I had 12,000 newtons, and for the normal force, I had 42,000 newtons.
All right, good. So, and again, they've shown you how to calculate the weight up here for some reason, just taking m times g. And then down here, they're helping you figure out what the normal force is. Remember, the net force is the centripetal force causing it to go in a circle. And the net force is just the vector sum of the two forces in your free body diagram. So since the normal force is larger, we would take normal force minus the weight force. You could also just say, like they showed, that up was positive. Now that's important. It wasn't really that important for part C, but and D, but it is important now. And so we could also just say, well, normal would be positive and weight would be negative. So if I add them, I'm basically subtracting. I'm adding a negative. But we know the net force is 30. That's what Sally told us about. And we know the 12,000 is the weight. So we would need to add those together to figure out what the normal force is. And the normal force then is 42,000. And if you stop and think about that conceptually, the car is, or sorry, the road is having to not only carry the 12,000 newtons of weight, it's also having to push with 30,000 newtons of force to make the car change direction. So the normal force has to be both of those things added together, the weight and the centripetal force, to make the car both carry the weight, or sorry, so it can carry the weight and make the car turn. Questions about E or F? All right, let's move on to number 2. In number 2, it says we got a car traveling over a hill now and at a constant speed still. Construct a qualitative motion map for the car. So again, it's qualitative. You do need to show, I guess, some quantitative measure that the arrows should all be the same length, at least for the velocities, and then all the acceleration arrows should match. But there's no numerical values required because it is qualitative. It just wants the quality. So again, the velocity vectors would be tangent to the circle and perpendicular to the acceleration vectors, and the acceleration vectors should all point into the center of the circle. And because the kissing circle matches the curve when you draw it underneath, we know the center of the circle is under the road. And then for part B, is the car accelerating? What direction is it accelerating? Very much the same as what we looked at on the previous page. The car is accelerating because the direction is constantly changing. At the top, the acceleration is down. We know because the car is traveling a curved path in the center of the circle of curvature, the kissing circle is below the car. All right. Questions on A or B? Much more conceptual for that part. All right. For part C, you should actually come up with a numeric answer. So go ahead and put your answer in the chat again, and in the classroom, be prepared to share. Anybody else have an answer for this one? Evan, did you get an answer for this one?
Yeah.
So I'm seeing a couple of different options here in the chat. I don't know how well you can see the chat. I've got a few people saying around 89,000 and one person saying around 7,000. Which of those did you come up closer to, or was yours completely different?
I had 6,900 newtons.
Okay, so you were closer to the 7,000. Tell us how you solved that one, Evan. What did you do?
I converted the kilometers per hour into meters per second. And then I did mass times velocity squared over radius. And plugged all those numbers in and got that.
All right. So if you didn't get the closer to 7,000, then probably forgot to convert to meters per second. And that is an easy mistake to make. And that is also something that sometimes College Board throws those little wrinkles in, especially for vehicles. They often give them in kilometers per hour. But if we think about what the units for newtons are kilograms times meters per second squared. So kilometers per hour doesn't match with meters per second. So we have to convert the kilometers to meters and have to convert the hours to seconds. So you can see here on the key, they've done that by taking the 43 kilometers per hour times 1,000 meters per kilometer and times 1 hour per 3,600 seconds. And then that gives them about 11.9 meters per second. Now the units match. So one of the things a lot of students have asked is, do we have to write our units in the problem while we're solving it, or do we just have to have units on our answer? And technically speaking, for the grade, you only have to have the units on your answer. But this is one of those scenarios where if you actually wrote the units out, you might recognize, oh, wait a minute, the radius is in meters, but the speed's in kilometers. Something doesn't match here. And you can actually see for yourself that there's going to have to be a conversion. Whereas if you just plug the numbers into the equation and you don't think about the units, it's really easy to make this kind of a mistake. And it is the kind of thing that College Board likes to throw in there as a little twist. So my recommendation is always use the units. Even if you just use it on the first step where you're plugging the numbers in, at least you have that one opportunity to recognize whether the units make sense and match or not. So it just gives you that checkpoint. I use them all the way through when I solve problems, but I understand that sometimes that feels cumbersome, or sometimes it's hard to, there's just so much on the paper, it's hard to see what you're really doing. But I would at least challenge you to put it in the first substitution step, even if you don't carry it on down through the rest of your work. All right, and then for part D, construct a quantitative force diagram for the car at the moment it's at the top of the hill. So we're still going to have normal force, and we're still going to have the weight force. And will the weight force change, or is it still going to be the same as the prior scenario?
I think it'll be the same.
Okay. Yeah, it's the same car, has still 1,200 kilograms. So the weight will still be the same. It'll be 12,000 newtons. That's the same as what we saw in the previous problem. In the previous problem, at the bottom of that valley, the normal force had to be much larger than the weight, because it had to carry the weight of the car plus force the car to go in a different direction. In this case, is it going to be more than the weight or less?
Less.
Yeah, it's going to be less, because in this case, the car's inertia isn't pushing it into the road, right? The car's inertia isn't fighting the movement of the road. Gravity is actually helping make that curve. So, and if you think about it just practically, if you're riding in a car and you go up over the top of a hill, you feel lighter in your seat. And the way you feel is the normal force. That's the apparent weight. Your weight feels less as you go up over that hill. So that means the normal force is going to be less. So if we pull that together, we know the net force is going to be the weight force minus the normal force. In this scenario, the weight force would have to be bigger. And we know that the net force is the centripetal force, which we just found, 6,800. And we know the weight force is still 12,000. So if we solve the equation for normal force, we end up taking the weight minus the centripetal net force. And so the normal force is only 5,200. So the car kind of feels lighter on the road. You feel lighter in your seat because the inertia of the car is actually upward. And so while inertia is not a force, it does help us conceptually think about the fact that the car's inertia would be carrying it upward, and its gravity is what keeps it on the circular path of the road. So the normal force doesn't have to bear the full weight of the car, since the weight is actually contributing to the centripetal force. So the way they phrased it here is the forces are not balanced. The net force is down. For the net force to be down, the downward force must be larger than the upward force. Since the pull of the earth on the car is down, it's larger than the upward force of the road. Questions on number 2? All right, for numbers 3 and 4, I'm going to put you in breakout groups for those of you that are on Zoom. And we'll have you guys work in groups of 2 or 3 and discuss 3 and 4, see if you can answer them, give you about 8 or 10 minutes. And for those of you in the classroom, you'll just have a conversation in the classroom. So in the class, if you would like, you could, work over on the whiteboard, just try to keep social distanced, or you can just stay in your seats and work on your paper and just converse about it, whatever is easiest for you. It's fine if you want to use the whiteboards to discuss it. Just try to maintain some social distancing. If you do that, though, when you're done, make sure you erase the whiteboard so we don't give anything away to the next classes. In the Zoom rooms, obviously, if you want to use the share screen whiteboard, you can. If you just want to talk it through, your choice within your groups, how you want to do that. So let's go ahead and get you into groups. Try to finish questions 3 and 4. All right, so group 1, you've got 3, group 2 is 2. I'm just making sure that the sub and myself aren't factoring in here too much. Okay, so everybody's got at least 2. We're good to go. Everybody understand what to do? Finish 3 and 4? All right, off you go.
Of an unbanked road, draw a force diagram of the car coming towards you as it is turning. which force provides the force. Turning. Yeah. So then there's.
Showing that and the forces.
Yeah, then there's a force pulling it in. I think it's weirder than that.
But it's not on, it's not on a bank. It's just on a plane.
Yes, it's just friction. You've got accelerations that way. And then force down this way. Yeah, I guess it is friction because the wheels turn and they're going the opposite direction. So the wheels are,
Yeah, it's friction.
when you go forward, the wheels are running on the ground backwards so that the friction pushes you forward. If that made any
Yeah,
sense?
No, that,
So when you're going, the wheel is going that way, so the friction force is that way, and that's what.
Yeah.
Yes.
Friction force are going. All right.
Ours. Yeah.
If it's towards the center of the turn, it's going this way. Then part of it. Normal force.
Yeah, the normal force.
That's gonna look like. On the friction.
you still have the friction.
Yeah, it's
It's
just
just angled.
not needed as much.
Wait, it's not angled.
Well,
Yeah, it's perpendicular to the surface.
it's like this. It's not angled, but like when you look at it, it says
Does the friction accelerate? down?
Yeah, because you're turning your wheels in towards the downward thing.
Okay.
But then the non-existence, typical inertial thing keeps you from falling in. It's just qualitative, right?
Yeah. Just. Oh,
Yo-yo trail.
A true friend.
And that shows like.
All right, so I was able to eavesdrop in, obviously, in the group that's in the classroom. I could hear their conversations, but I would like to hear from the other groups as well and see what you came up with for some of these things. So for question 3, part A, when it talks about the car being on flat road and which force would enable it to turn, and then drawing your free body diagram. Kyle, tell us a little bit about what your group discussed.
For 3A.
Yeah.
So we thought that the normal force and gravitational force would be equal, and then there would be a third force to the right of friction force, which is making the car turn.
All right, good. I'll go ahead and share my answer key here as well, so you can kind of compare notes, but that one's probably straightforward enough that I imagine he described it well too. Imagine that you can picture that, but in case it's a little bit difficult for you to picture that, the way I heard it is exactly the way I see it on the key. That the normal and the gravitational force are equal and opposite, and you've got that friction force to the side. And then I'm curious, Rocky, did you guys talk at all about whether it would be static friction or kinetic friction?
No, we didn't talk about that. But would it be static?
Yeah, it would be static. What drew you to that conclusion?
Well, I just remember last class or the class before that, you were saying how if it was like for kinetic, they would it would have to be like sliding, like if the road was icy or something, but since the tire's like gripping it, then it's static.
Yeah, that's it. That's exactly it. So great memory. So the static friction is when things grip, when they stick together. And then kinetic generically, that word means movement, but kinetic friction more literally means sliding. And so unless the surfaces are sliding across each other, it's not considered kinetic friction. And the whole goal here is that the tires don't slide. We want the tires to stick to the road so they don't slide so that they can make the curve. So this indeed would be static friction. So we would have an acceleration and therefore a net force to the center of the circle. Good. Let's see. Cade, tell us a little bit about part B. What kind of things did you guys discuss for part B?
Well, for part B, as well as having the friction force turning it right, it also has a bit of the normal force since the car is slightly turned right and the road is tilted as well.
Okay, very good. And then Nat, when you guys were doing this, or maybe just you personally, I don't know if you all drew it the same way exactly, but did you use flat axes for this one, or did you use angled axis? What strategy did you take?
I used an angled axis.
Okay. So if you use an angled axis, which one has components? Which force has components?
The normal force and the friction force.
So you left the x and y normal straight?
Yeah.
Oh, okay.
Wait.
Okay.
No, it was like this, and then so the normal force would follow the y-axis, but then the gravitational was like straight and wouldn't follow the axis.
Okay, good. Okay, so yeah, maybe you misunderstood my question. And so way you described it right there is exactly what I was expecting. So the normal force goes along the y-axis because you angled it, and the friction goes along the x-axis because you angled it, but the weight force doesn't. Is that right? Am I saying it right? Okay, good.
Yeah.
That's actually the way I drew it as well. That's not necessarily the only way to, but I was just curious if anyone did that. What I want to talk about, though, to wrap up this 3B part is that the friction could be up the slope or down the slope, depending on how fast the car is going. All right, so I want you to imagine that. And let me show you something else first. Let me scroll down, and in case you're having a hard time picturing what I mean and what Nat was saying, we were on the same page and we were still having a hard time. So it may be hard for some of the rest of you too to figure that what we're talking about. But the normal force here is on the y-axis. I angled it as well. I didn't really care for the way the key showed it, so I drew my own on here. So the normal force is on the y-axis. And the weight force is not. And I have intentionally left the friction force off for now because I want to talk to you about how it could be either direction. Okay. First, I've seen this kind of a question pretty frequently. And a common thing that they'll ask is for you to figure out what speed the car would need to go on this banked road so that it doesn't need friction. If the road is banked, then so depending on how you drew yours, if you use a traditional X and Y, then the X component of your normal force would be supplying the centripetal force to keep it going in a circle. If you drew it like Nat and I did with the angled axes, then it's the X component of the weight force that's pushing it back to the center. And so if you're going slow enough, it could be a purely icy surface, but if you're going slow enough, that normal force, that X component of the normal force, or if you drew it this way, the X component of the weight force would be pushing it back to the center of the circle, and you wouldn't even need friction. Now, especially for those of you that drive, and even if you don't drive, if you've watched on off ramps and on ramps, you know that those are often banked and definitely curved. And so you see cars not going really slow, right? So they need friction. But there is a slower speed where you could go and actually eliminate friction. And if that were the case, the free body diagram would look just like what I've drawn here. There would be no friction if you went at that perfect speed where friction wasn't necessary, where the normal force or weight, whichever way you drew it, that X component would be sufficient to provide the centripetal force. But if it was providing centripetal, or if the friction was helping, so let's say you are driving faster like a normal person, and you're going around that curve, the normal force or the X component of the weight, whichever way you drew it, is pushing back to the center of the circle. And the friction would also be pushing back to the circle, pushing back, because the car's inertia, the car would be trying to slide up the slope, right? The car would be trying to slide up the embankment if it's going fast. And the friction would be not allowing the tires to slide up the embankment. So if you're driving fast, the friction looks like this. The friction force is the same direction as that X component, and both the things together, the X component of the weight or normal force and the friction force, are both helping to push the car back to the center of the circle if the car is moving fast. If the car is moving at a very particular speed, then there would be no friction. If it's going slower than that speed, then it's all, instead of thinking about it going slower, thinking about it being parked. If the car was parked on an embankment, the car's natural tendency would be to slide down the bank, right? So if there's friction, it's not actually keeping the car from going up the embankment, it's actually keeping the car from sliding down. So if the car was stationary or driving extremely slowly, then the friction would be up the hill so that the car doesn't slide down. So that would be the friction force if it was stopped or super slow. So they could ask you about a lot of scenarios on an embanked road, and friction force is always going to resist the movement if it's static friction. And so there's a few ways you can think that through. There's a single perfect speed where you don't need any friction and you wouldn't even draw it. If you're going normal, faster speed, you need friction to help make the curve so it's down the slope towards the center of the circle. And if you're going super slow or parked, the friction is up the hill to keep the car from sliding down the embankment. So lots of things to consider there. Any questions about that? We went well beyond what this question asked, but I want to prepare you for lots of scenarios you could see. All right. Let's see. Johnny, tell me something that you and Andy came up with for the yo-yo problem. You don't have to explain the whole thing, but just give me a couple bits of what you talked through.
So basically, we had our velocity going in the direction of the arrow that they gave us. And then we had the acceleration pointed towards the center of the four quadrants, or I guess you can say where the starting position of the yo-yo. And then we just had a question. How would we draw the force of gravity for this if we would even need to draw that? Because we were kind of talking about if it would go towards the direction of the ground, but at some points the acceleration was already pointed in that direction. So what would the force of gravity be here?
Yeah, good question. So I'll answer it with a question. What causes gravity? And anyone can answer. It doesn't have to be Johnny and Andy. Anyone can answer. What causes gravity?
The traction, like how heavy something is, it kind of like pulls it.
So the mass helps us figure out the gravitational force, but like on Earth, just speaking and generally on Earth, what causes that gravitational force? What's that?
A rotational pull.
The rotational pull actually affects it, but it's not what causes it. That's actually a problem we're going to talk about after break. Why are we attracted to the Earth? What about the Earth pulls us?
It's massive mass
Yeah, it has a huge mass. And so the mass of the Earth is what creates the gravitational field. And so the mass of the Earth would always be below us. So if that's what's causing it, the gravitational force should always be down, straight to the center of the Earth. So Jack, you guys in the classroom, what are some other things you guys talked about? So they got us going there. Good discussion that the velocity would be kind of tangent to the circle, always pointing in the direction the yo-yo is going, and that the acceleration would be to the center of the circle towards the person's hand. But tell us some other things you guys talked about.
So we kind of just like, for me, it helps to visualize things. So I kind of imagine like the guy spinning it. And so we did like individual, like top descending side, bottom ascending side. And then just like what they said, they just kind of drew arrows, and so did we. And then just labeled them with the force of weight or gravity, and then the string force. But that was like mainly it.
Yeah, and the weight was always pointed down, but then the tension or string force would move around, sometimes working with the weight. And so then the tension force would be much lower, or it'd be working against the weight, and so it could be much higher.
Okay, good. So that kind of goes back to what Johnny and Andy were talking about too, that it's a little confusing when it's going in the same direction as, and so you start wondering, is one of these things wrong? But sometimes they do go in the same direction. So let me show you the key here so you can sort of visualize several of the things that both groups have talked about. On this picture, they did not draw the velocity vectors or the acceleration vectors that Johnny talked about, which that's fine to add those velocity and acceleration vectors. They aren't free body diagram components, but they might help you figure out how to draw the free body diagrams. So all they've done here is draw the free body diagrams and then just use words to explain them. So like Ethan was saying, well, both groups actually were saying the weight is always down. So your FG is always straight down, but the tension is changing. And like Ethan was saying there at the end, the tension force at the bottom has to be stronger because it has to be strong enough to hold the weight of the yo-yo, but it also has to be strong enough to pull the yo-yo back towards the center. It has to accelerate it back into that circular motion against its inertia. So the tension would be stronger at the bottom. And if you've ever swung a yo-yo in a circle, you can kind of feel that on your finger. If you haven't, try it this week. Get a yo-yo, put it on your finger and swing it around. And at the bottom, you can feel it pulling harder on your finger, but at the top, it doesn't feel like it's pulling as hard. And that's because at the top of the circle, the tension is down to the center, but so is the weight. And so if you're spinning it really slowly, there's a point, there's a velocity where that tension could be zero. And at the very peak, you wouldn't even feel it pulling on your finger at all. But if you're spinning it fast, you would feel it pulling, but it would still feel less tight at the top, or pull less with less force at the top than at the bottom. Because at the top, the weight's actually helping. At the bottom, the weight's fighting the tension. And so you feel that change. On the two sides, they're perpendicular. The weight force and the tension in the string are perpendicular. So the tension has nothing to do with the weight at that point, and the weight has nothing to do with the tension. The tension is purely about changing the direction of that yo-yo to keep it in a circle. And on the left and the right sides, the magnitude would be the same. They would just be pointing in the opposite directions. And they should be less than the tension at the bottom, because the tension at the bottom is where it's going to be maximized. That's where it's bearing the full weight of the yo-yo and fighting against the inertia of the yo-yo. In the sides, it's not bearing the weight at all because they're perpendicular, but it is still fighting the inertia of the yo-yo to pull it back into a circle. All right, any questions about number 4? All right, so that's good for worksheet 2. We can sort of put that one to rest. I do want to just begin to talk about one of the questions on worksheet 3, just to sort of get your process started. And then that's probably all we'll have time for. We'll just take maybe 5 minutes here to get started, and then we'll let you go for the day because we're almost out of time. But I would encourage you to go through worksheets 3 and 4. I would encourage you to practice several of those questions. And like I said, I'll post the keys here. When our class is done, I have a little bit of a lunch break. I think you do too. So I'll post the keys on Axis as well. So if you want to practice these over break, you can have some answers there and know. Actually, you know what? Maybe I'll wait till I might not do it today because I don't want them to necessarily be there for my other classes who haven't met yet. So I'll wait and do it tomorrow sometime so my other classes don't have an advantage. I don't want them to see the key before we have some discussion. So, but I will definitely put them on there before the break so that if you want to work on them over the break and practice, you can do that. You can always obviously work on them beforehand, but I want you to be able to check your work. So let's real quick just take a peek at worksheet 3 and just the very first question. In this first question, we've got a woman that's flying acrobatic maneuvers with the plane, and it asks us to construct a quantitative force diagram or free body diagram of all the relevant forces on the woman flying the airplane when upside down at the top of the loop. So just to make sure that everybody's looking at the same thing here, this is the worksheet, worksheet 3, circular motion examples. And we're just taking a peek at this number 1. So we're focusing on the woman, not the plane itself, but the woman, the pilot. So what are the forces on the pilot? What are the forces acting on her?
Force of gravity.
Yeah, she still has weight, the gravitational force still pulling her to the center of the earth.
And the force of the plane's lift.
Is the plane's lift doing anything to her directly?
I think so, because if the plane was going, like, pushing up in its frame of reference, then it'd be pushing up on the woman, right?
But is the lift pushing on the woman?
I guess no, not directly, but the plane is pushing on the woman.
Right. So we need to get, you're like, what is that thing? So many steps to Kevin Bacon. You're like one step away from what we would call it. So the lift is what causes it indirectly, but what is it directly?
Just like contact push force.
Yeah. So what do we typically call that surface pushing force?
I got this. Normal force.
Yeah, there we go. So yes, indirectly you are correct that it is the lift of the plane and the movement of the plane that generates it. But if we're going to label what it actually is on the woman, it's that surface contact of the seat, really, and it's just the normal force of the seat. And so that's the tricky part. The more complicated these problems get, you really have to focus in on what the dot represents, and then what are the exact forces on that dot. So sometimes you end up being a few steps away, and it's not that it's unrelated, but it's not quite the right force, and then it can really be confusing when you're trying to solve it. So that's why I wanted to kind of get you started on this one, so that once you have this one kind of fleshed out, it can help you with other similar ones. So this woman has the weight, which is just caused by the Earth's mass, nothing to do with the plane at all, right? So the weight of the woman would just be based on her mass, which it gives us is 55 kilograms. So we can just take that 55 kilograms times G, and we know the weight force. But how are we going to find that normal force? There's no formula for normal force.
We know the net force is the centripetal force, and we have the velocity and radius, so we could find the centripetal force and then subtract out the weight.
Good. So if you're having a little trouble tracking that process, what we're saying is we know it's centripetal because there's circular motion, and we can find the centripetal force acting on the pilot because it's m times v squared over r, and we have m and we have v and we have r. So we can find that centripetal force. But the centripetal force for objects in circular motion is the net force. So that centripetal force or net force will equal the vector sum of the normal and the weight forces. So let me switch to the key so you can kind of see it instead of just hearing it. So this question really only asks us to show what's way over here on the left. It asks us to make a quantitative force diagram. But to quantify that normal force, we're going to have to do all this work that's over here on the right. First step, find the weight. So just take the mass times G, 550. All right, that's easy. We've done that tons of times. So that's the first step. And now we know the FG value on our quantitative free body diagram is just 550. Now you'll notice that they decided for this problem to make downward the positive direction. That way they don't have to make all these forces negative and deal with a bunch of negative signs. You don't have to do that. You could make it normal and make everything negative, and the negatives will all cancel. But if you want to avoid that hassle of using a bunch of negative numbers, remember, you can always redefine which direction is positive. And they have chosen to redefine down as positive for this scenario. And remember, this free body diagram is a point in time. It's not the airplane pilot at any point. It's right here at the top of the circle. All right, so then they're doing the next step. They're saying, well, the net force is centripetal because it's uniform circular motion here. And all net forces are m times a, but in this case, the a would be centripetal acceleration. And centripetal acceleration is v squared over r. Now we do have to do a little conversion here because once again, they've thrown our velocity at us with kilometers per hour. So we do have to convert it to meters per second so that we can have all of our units match up with newtons properly. So we have to convert that 235 into meters per second using 1,000 meters per kilometer and 3,600 seconds per hour. But then we can figure out, okay, well, that centripetal force is 617, which if we want to round it off to 2 sig figs at this point, it's 620. And then we have our net force equation there. The net force is weight plus normal. They're both going the same direction, so we should just add them together. And down is positive according to the way they've defined it, so they're both positive values. The net force is centripetal, so that's where the 620 goes. The weight force is the 550 we found just using G, and the normal force is the only thing we're missing. So we just solve for normal force. So the seat's only pushing on her with 70 newtons. And that makes sense because the seat doesn't even have to bear her weight. She's underneath it, right? So the seat is not bearing her weight at all. The seat is only pushing her back to the center of the circle. And there is a certain speed where she would be weightless, right? There is a certain speed where that normal force would be 0. But at this speed, it's not 0, it's 70 newtons. So there's a little bit of force. She feels the seat pushing against her just a little bit, but not a lot. So if she went just a little bit slower, she would get a normal force of 0 and she would feel weightless at that point. All right, we're out of time, but I wanted to walk you through another example just so you've seen a lot of different kinds now. And again, I'd encourage you, work through worksheet 3, work through worksheet 4. Sometime tomorrow, once my classes are done meeting, I'll put the keys onto Axis so you can look at those answers over the break. Encourage you to do that review for the exam while you have some time. Hopefully you have some time. I hope you have a wonderful break. If you have some questions for me about this problem or anything else, I'll keep the Zoom running for a few minutes, but we are out of time, so you're dismissed. Enjoy your winter break.
Thank you.
You're welcome.
Thank
See you
you.
guys.
Thank you, Mr. Webb.
You're welcome.
Thanks, Mr. Webb.
Have a great break.
Thank you.
I guess Evan, I'll see you, Evan, tomorrow, but I think the rest not for a little over a week. So
I don't think we don't have to, but I think we recommend it.